Hey there, in today's video I'll talk about how one can prove that a sequence is eventually in a set. So let's look at the statement that we want to prove. For each natural number little n, let the sequence a sub n equal to 3 plus 7 minus n all divided by 2. Then the sequence a sub n indexed from 1 to infinity is eventually strictly negative. That is, the sequence is eventually in the interval negative infinity to 0. To prove this, we'll need to use the following definition. A sequence a sub n of real numbers is eventually in the set A, which is a subset of the real numbers, if there exists a natural number capital N, such that for all little n greater than or equal to capital N, our sequence is in the set A. Now let's go back to our statement and identify what A is. We're told that A is eventually in the interval negative infinity to 0. So let's make this our set A. If we take a quick look at the definition that we are using again, what this means is that we will need to determine a capital N in order to complete our proof. But before we do that, let's look at the several elements of the infinite sequence to get a sense of how it behaves. After all, the statement is telling us that at some point every element will be negative, but when? Let's try to figure that out. Let's consider the sequence that we're giving in the statement. A sub n is equal to 3 plus 7 minus n, all divided by 2. And let's take n to equal to 1. What this means is that a sub 1 is equal to 3 plus 7 minus 1 divided by 2, and this simplifies to 6. Now suppose that n is equal to 2. And this simplifies to 5.5. Now I'll do this for n equals 3 and 4, and we'll kind of get an idea of what's happening. And this simplifies to 5, and n equals to 4, where a sub 4 is equal to 3 plus 7 is 4 divided by 2, and this simplifies to 4.5. So notice that the sequence is dropping from the look of it, and it's approaching the interval negative infinity to 0. But what choice of little n will every entry in the sequence produce negative quantities? To phrase this differently, when will the given sequence a sub n be less than 0? Which can also be written as let's work this inequality out in a way that satisfies our definition, meaning we want the little n on the greater than side. So subtracting 3 from both sides of the inequality, we get multiplying by 2, and then moving this little n to the right-hand side and the 6 to the left-hand side. And to make this resemble our definition, we could just write so what we just determined actually was our choice of capital N. The inequality insists that we choose a value of capital N such that it is strictly greater than 13. Then, let's take n to be 14. Since 14 is in fact greater than 13, so this is a valid choice. Keeping in mind our choice of capital N, recall the 4 elements of the sequence that we found a moment ago, with the last entry being 4.5. If we continue in this way, when we get to A14, we find that it equals to negative 1/2. If we try A15, with some arithmetic, we get that it's negative 1. Which means that we're starting to see negative values, which implies that we are actually in the set A, or negative infinity to 0. Now that we found our natural number capital N and have an intuitive understanding of what it means for a sequence to be eventually in a set, let's begin our proof. Recall that our definition wants us to begin by stating the natural number n, and then conclude by showing that this condition is true. We could begin our proof by writing let capital N equal to 14. Suppose that for all little n, our little n is greater than or equal to capital N, which we just said was 14. We want to show that our sequence A sub n is eventually in the set negative infinity to 0. So notice, if we look at our inequality, n is greater than or equal to 14, we could work with that. The strategy at this point is to try to get the sequence A sub n on one side of the inequality. I know that sounds a bit vague, so let me just explain a little further. Notice that we have this negative n term in our sequence. Let's try to mirror that over onto our inequality by multiplying both sides of it by -1. And notice that the inequality sign changes. So we get, now if we look back at our sequence again, we have this 7 in this numerator part of this fraction. So let's carry that over onto our inequality in the proof by adding 7 on both sides. Now we can multiply both sides of the inequality by 1/2 to get and finally we could add this 3. And notice that that's actually starting to look like our sequence. And we say that this is in fact equal to our sequence A sub n, and what this reduces to after some arithmetic is -1/2. And it is indeed true that -1/2 is less than 0. And what this tells us is that A sub n is less than 0, which is essentially what we want to show. So now we could write our concluding statement. Hence, for all n greater than or equal to 14, A sub n is less than 0. That is, our sequence A sub n is eventually in the interval -infinity to 0. And we could just conclude our proof here. I hope this video has been helpful, and thank you for watching.